Hello, so in this video we're going to be looking at something called phase portraits. Okay, phase portraits, and these are really useful because they're a very visual way of looking at what solutions are doing. Okay, and phase portraits are actually really useful because they allow us to solve an ODE. Remember that an ODE is just simply a description of change. Okay, so for example, if we have something like dy by dt is equal to some function involving y, so anything, differential equation just basically models, models or describes change. All right, and so sometimes these ODEs are quite difficult to solve. So where phase portraits come in is they make things so much more visual. You don't actually have to solve things in kind of algebraic way or try and solve them in numeric way. You can just basically kind of try and draw what's going on with the solution. Draw what's going on with this, and you can kind of get all the information you need. So you don't actually need to solve it as such. Right. So basically, what I want you to consider is that I want you to consider this kind of graph. So this is t now. So we vary through t along this axis here. All right, and we're going to move. This axis here is going to be y. So a function y. Okay, and this is basically going to be the solution to this ODE. It's going to be the solution to this ODE. All right. So basically, what I need you to consider now is I need you to consider a graph like this. Okay, graph like this. Okay, now I want to basically try and model the rate of change of this graph. Now remember what the rate of change means. The rate of change. Well, the rate of change is just the gradient, right? For a straight line graph, the rate of change is just given by the gradient. Yeah, because it's fairly obviously if you have a straight line graph from there to there, the rate of change is going to be constant. So therefore, the gradient will give the rate of change. All right. So if you look now at this case, which is a curved graph, it's no longer a constant rate of change. In other words, the rate of change here is going to be quicker because it's a steeper gradient, whereas the rate of change here is going to be, slower because it's a more flatter gradient. All right. So, that's the kind of thing that we need to bear in mind. So obviously, the rate of change is changing as we travel along this graph. If we kind of move through time. So we move through equal steps in time. Let's say we move through equal steps in time. Okay, so this is say t0, this is t1, t2, t3 and t4. As we move from t0 to t1, what's happening in the y direction? Well, from t0 we move to there, from t1 we move to there. All right, so this is y of t0 and this is y of t1. Yeah, so from t0 to t1, remember these are equal size steps, so I tried to make them equal. Maybe we don't need t4 then. I'll stick it in. They've tried to make them relatively equal size steps. Okay, so from t0 to t1, we're moving by that distance. Whereas from t1 to t2, well, how far are we moving? We're only moving by kind of that distance. Okay, obviously I can't write that in. Okay, so actually I'll just get rid of this. So this is t1, y of t1. This is y of t2. Yeah, we're only moving by that distance. So in the same time period, okay, we're only moving by a small direction in that one. So therefore, the rate of change in that time period is going to be much smaller. Okay, and likewise, if we consider this time period, right, okay, the rate of change isn't as big as the first time period, but it's bigger than the kind of second time period. So it's this rate of change because we're moving by a slightly larger amount from the time period from t1 to t2. But we're not moving by the same amount as we move from t0 to t1, all right? And likewise, you could probably do t4 as well and see that you kind of get roughly, you get the same kind of analysis, same kind of deductions. Okay, so what I want to basically do is try and come up with some kind of way of kind of writing the rate of change because it's not going to be constant. Well, if you consider that, we've got a curve like that. A curve is just a series of straight lines, right? So if I draw a series of straight lines, sorry, no, that's bad drawing, something like that. Yeah, if you kind of zoom in a little bit, maybe not there, but maybe sort of somewhere like, a curve is essentially a series of straight lines, right? Because basically in the limit, as we zoom further and further out, so if we zoom in there, that's what perhaps that would look like, all right? And then we can zoom in further and basically see that it's effectively just a straight line. All right, so that's kind of the idea. As we zoom in further and further and further, as we magnify sort of a piece of a curve, it's going to become a straight line. So what we're doing, we have to consider a smaller and smaller section of the curve, okay, in order for it to then become like a straight line. Okay, so if we do that, then we can just write the gradient. You can just write the formula for a gradient. Okay, so what's the formula for a gradient? Well, it's change in y over change in x. Change in x. Okay, and we can actually give that a symbol, and we normally give it delta. So it's delta y over delta x. Except now we're considering such a small change. We're considering such a tiny change. You know, such a tiny change. You know, that's a big change. It's a tiny change. It's so close to zero. So we kind of give that not small letter delta. Yeah, basically, big change we write capital letter delta. Small little change we write little letter delta. For tiny change that's basically zero. You know, if we considered any smaller change, there'd be nothing there. Yeah, we wouldn't be moving at all. We write that as a d. Okay, so now dy by dx. All right, so you've seen this. This is kind of the idea behind differentiation. Yeah, hopefully if you've seen differentiation from first principles. Well, what is the change in y by change in x? Well, it's not exactly, but it's approximately. So we've got a curve. Okay, we've got a curve, and we're considering such a small, you know, we can do such a small section of this curve that it's basically, you know, it's basically zero. Let's say, oh dear, there we go. Considering such a small section of that curve that it's basically zero. Let's say. All right, so basically what we end up with is something like this. Okay, so we end up with a curve. So I've magnified this up. Okay, so this is my first time period. I'm going to call that t. And I'm going to call this time period over here, or this time here. So this is t still. This is y. So this time here is going to be t plus some movement. So we're moving such a small distance. And we're going to call that small little distance h. Okay, we're obviously going to have a corresponding y value. So this is going to be y of t. And this is going to be y of t plus h. Okay, so now what is the gradient of this straight line? Well, hopefully you can see. So I've got dy by dx, that's the gradient, yeah, is approximately equal to, well, it's change in y, which is y of t plus h, okay, minus y of t, that's my change in my y direction, over my change in my x direction. I've just said that I've moved in the x direction by h, okay. So this is effectively roughly what I get for differentiation for first principles. Of course, if it's truly differential first principles, if I want to make this exact, I have to write the limit as h approaches zero. So I basically have to show that h is getting smaller and smaller, that we're considering such a small section, of the curve that it's practically zero. It's practically zero. So this section here is basically getting smaller and smaller. So this section here is basically getting smaller and smaller. All right, smaller and smaller. Okay. So now we can consider different scenarios. So let's consider the case when dy by dx. Is less than zero. Well, what does that mean? Well, that means if it's less than zero, then our rate of change is negative. All right, so our rate of change is negative. So in other words, we have a downwards gradient. So therefore, if we have a downwards gradient, then, you know, if we've got a downwards gradient, then, so we've got a downwards gradient. Let's just draw our graph out again. So we've got t here and we've got y here. Okay, so we've got downwards gradient. So we're looking at something like that. Okay, which basically means this is t plus h again. This is t. Yeah, this is y of t, and this is y of t plus h. Okay, so what does that mean? Well, it means that y of t plus h, yeah, is got to be less than y of t. So in other words, y of t plus h has got to be below y of t if it's going to be a downwards gradient, negative gradient. Okay, if that's the case, you know, y of t plus h, the y value at t plus h, this value over here, this y value here, has got to be less than the y value at t. All right. Now let's consider the case when we are not changing at all. So dy by dx is equal to 0. Well, what does that mean in terms of this? Okay, so again, we've got y, we've got t. What does that mean? Well, we're not changing, so therefore we're just on a flat line. Okay, so fairly obviously this is t plus h. Okay, so y of t plus h is the same as y of t. Yeah, so y of t plus h is the same as y of t. That's the only way that we can get a straight line. Okay, if the y values at both of these time points t and t plus h are the same. Yeah, these two values are the same. Okay, and likewise, let's consider the last case. So fairly obviously, if this was less than 0, this was equal to 0, then fairly obviously we're going to be considering greater than 0. Okay, so in other words, we get this thing going on. So this is y, this is y, this is t, this is t plus h. Well, it's exactly the same thing as we got before. If we've got an upwards gradient, then we've got a positive gradient like that. Okay, so therefore y of t plus h has got to be greater than y of t. Yeah, so y of t plus h has got to be greater than y of t. Okay, cool. So basically, you know, this is what we've got now. Okay, so this is what we've got, and this is what we're going to go bear in mind for the next part of this video. So what we're now going to try and do is try and sketch what's known as the phase portrait. Okay, so effectively, if we go back to what we started with, you started off with derivative with respect to, did we start with dx or dy? Can't remember. Sorry, yeah, these are supposed to be dt's. I think I made a mistake earlier on. They should all be t's instead of x's because we haven't got any x dependent variables. Sometimes we use x, sometimes we use t, but here we use t because we're differentiating with respect to time. Okay, because these functions here are dependent on time. So yeah, sorry, that was my mistake. So these should be dependent on time, and all of these up here should be dependent on time as well. All right. So we had this, and this is equal to some function which is dependent on y. All right. So basically, what we want to try and do is we want to try and draw the phase portrait. So in other words, I'm going to let this axis here be y. I want this axis here to be y, and this axis here is kind of, you know, let me just try and find a good one. Yeah, so this is y, this is t. Effectively, this axis, you know, this bottom axis that I had drawn out down below was effectively this kind of thing condensed into one axis, if you like. Okay, because this is kind of the difficult thing when it comes to differential equations. You kind of have to condense, you have to kind of squash axes together, okay, and then kind of expand them at a later date. In order to consider them properly. So this is y, and this is how y changes with respect to time, okay, which of course is just some function of y, okay, and that kind of makes sense now. So we've got the function of y on this axis here, and we've got the y value along this axis here. All right, so basically, you know, let's assume that we've got some function. Let's assume we've got some function like this. Up, down. Okay, and basically the equilibrium points are going to be wherever we cross the x-axis. So in other words, when this thing is equal to 0, when the rate of change is equal to 0. So this thing here, which is the rate of change, is equal to 0, is going to be here and here and here. So these are my equilibrium points. I'm going to call them A, B, C, and D. Okay, cool. So let's look at what happens with my rate of change. So down here, well, let's look over here first of all. Here's my rate of change is above the axis. My rate of change is above the axis, so therefore my rate of change is positive. You know, my dy by dx, my dy by dt is positive. It's above this axis here, so therefore when it's positive, that means that y of t plus h is going to be greater than y of t. So if I kind of, you know, if I just draw this down below. Right. If I now draw out what's known as a phase space, which is basically just all the points which y can sort of take, y can travel to, this is y, which y can move to. Okay, so effectively what I'm trying to do is I'm trying to model, you know, I'm just trying to use this axis here to kind of show how y moves in time. So let's assume that, you know, as we move forward through time, dy by dt is positive. So therefore, let's say if I want to move from one step to the next, this is t, and this is t plus h. Okay, sorry, y of t, and y of t plus h, y of t and y of t plus h. As you know, I'm effectively moving forward in time. Okay, so between time steps. So if I draw my equilibrium points on like that, there we go. Draw my equilibrium points on. Okay, so this is A, B, C, D. Then as I move forward through time, what I'm basically saying is if it's positive, then my next time step is going to be to the right of my previous time step. So imagine I'm starting here, okay, and I'm moving forward through time, all right, and I'm basically saying that because, you know, to the left of my equilibrium point, my next time step, which is y of t plus h, remember that's my next time step, I'm moving forward through a time step h, so I start here, so t, and this is t plus h, okay, I'm moving forward through a time step, if you like, of h, okay, then I'm basically saying that my my next y value is going to be bigger than my previous one, so in other words, I'm moving in this direction. But if you look down here now, I'm negative, so my rate of change is negative, so that means when my rate of change is negative, that my next time step is, or my next y value at my next time step is going to be smaller than the time value at my previous time step. So in other words, I'm moving to the left, yeah, because this is as y gets bigger as we move along to the right. So therefore, if my previous time step was bigger than my next time step, therefore I must be moving in this direction. because in other words I'm getting smaller as I move forward through time. Okay, now let's look at this thing up here. So now I'm looking at the case when I'm positive, so my dy by dt is positive, right? So that basically means when my dy by dt is positive that my next time step is bigger than my previous time step. Okay, so in other words I'm moving to the right again. Okay, and let's kind of look at this next thing now. Okay, so again, dy by dt is negative, so therefore I must be moving to the left. My next time step is smaller than my previous time step. Let's look up here again. So here I'm positive, so therefore my dy by dt is positive, so therefore I must be moving to the right. My next time step is getting bigger than my previous time step. And what happens at my equilibrium points? Well, my equilibrium point is when dy by dt is equal to 0. So when dy by dt is equal to 0, that means that my next time step is the same, so my next y value is the same as my previous y value. Okay, so in other words, I'm not moving. Okay, so effectively this is if you like my phase portrait. It's modelling how the y value changes with respect to time. Okay, so as I move forward through time, I'm moving towards this equilibrium point. As I'm to the left of this equilibrium point, moving towards it. And then here, so A, I'm moving towards my equilibrium point. B, I'm moving away from my equilibrium point. C, I'm moving towards my equilibrium point. D, I'm moving away from my equilibrium point. Okay, and I can actually give those special names. I can say that A, and C are asymptotically stable. Sorry, that's not right. Asymptotically stable. And all that basically means is that I'm moving towards my equilibrium point. Right? But here at B and D, I'm unstable. I'm unstable because I'm moving away from my equilibrium points. Alright? So that's kind of the difference between stable and unstable. If I'm stable, I'm moving towards the equilibrium points from both sides. That's why it's called asymptotically. I'm moving towards the equilibrium points from one side. If I'm just moving towards the equilibrium point from one side, then I kind of don't know what the other side is doing. For example, I could have a case, if I had an equilibrium point here, where I'm moving towards it from one side, but then I continue moving away from it the other, and then that would still be an unstable case, because I'm not actually stopping at the equilibrium point. There's no, it's stable if I'm coming from both sides. If I'm unstable, I'm only coming in from one side, or I'm moving away from it. Okay, and actually there's another type of asymptotic. It's not just asymptotically stable. There's also Lyapunov stable, which I'll just kind of very quickly talk about now. So Lyapunov stable, okay, which is essentially where you're kind of you kind of come in from one side, okay, and then you kind of move past it a little bit, but then you kind of almost bounce back, okay, and you end up basically just bouncing back and forth, over and over and over and over again. So you end up basically bouncing back and forth over and over again, and because you're so close to the equilibrium point that you basically say, do you know what, you're basically at the equilibrium point. So we're so close that we're basically at the equilibrium point. So we're going to call that Lyapunov stable. Okay. So now let's look at this kind of phase portrait and try and look and see what y of t look like. So essentially, we're trying to, at the moment we've got y and t collapsed into one axis. What we're now going to try and do is uncollapse it or uncompress it. So here's y and here's t, and we're going to come up with what's known as a solution. Okay, so let's have a look. So we've got 0 here, so let's continue this down a little bit more. So let's say we have, what were our equilibrium points? We had A, B, C, and D. Okay, so A, B, C, and D. So here's A, here's B, here's C, and here's D. All right. So A fairly obviously was to the, if you look back up here, A was to the left of the equilibrium point. Yeah, A was to the left of our equilibrium point. Here's 0 on our y-axis, if you like. So on our y-axis down here, A should be the left. Okay, and then obviously we go B, C, D, and D. B, C, D, and so on. So we move to the right, so therefore we're moving up, if you like. So all I've basically done is I've moved my y-axis that was down here. He was 0. He was A, B, C, and D. All right. So here was my original y-axis, and all I've basically done is I've just where was 0? So I put that as 1. Here's 0 here. Okay, and all I've basically done is I've moved it, rotated it through 90 degrees. Okay, and I've just stuck an extra t-axis to show how we're moving through time. So effectively, I'm using this thing now. To try and kind of uncompress it and look at what the original graph looked like, and that's called the solution. All right. So this is y, and this is t. Right, now we said up here, let's go back up here. So we said up here that at A, we're moving towards it from both sides. So as we move forward through time, we're moving towards A. Okay, so we move forward through time, we're moving towards A. So maybe, if I draw the line, we're moving towards A. So therefore, we're doing something like this. So we're moving something like this. Okay, so moving towards A. And we're asymptotically stable because we're coming at it from both sides. But we don't know at which point we are actually equal to A, which is why we say asymptotically. Because theoretically, we may never reach A. We may get really, really close to A, but we may not actually reach A. We don't know whether we actually reach A, at what point we actually reach A. Okay, we can have the line y equals A as well. The line y equals A as well, because of course we know that there is an equilibrium point at y equals A, and likewise for B, C, and D. So I'm going to actually draw those lines in now. So these are the lines when the dy by dt, if you like, is equal to 0. So there's an equilibrium point there. Okay, now let's look at B. Let's look at B. Well, we're moving away from B, when we're below B, which is, if you like, to the left, because I've rotated it 90 degrees. This axis 90 degrees to the left. Then when I'm below, I'm moving away from it. And when I'm above, so to the right or above, I'm moving away from it as well. And I'm moving towards C. So otherwise, I'm having this thing going on. So I'm moving away from, I'm moving away from B in both cases. I'm moving away from B here, and I'm moving away from B here. All right, so let's have a look now. So let's look at C. Well, in C, I'm moving towards C here, and I'm moving towards C here. So above and below C, I'm moving towards it. All right, so I'm moving towards it here. That's fine. I've drawn that one in already. I've drawn this one in already. So now I've also got this thing going on as well. So I'm moving towards C. That's fine. And then D, what's happening towards D? Well, I'm moving away from it in both cases, above and below the line. So I'm moving away from it here, okay, but I'm also moving away from it here. Okay, and this is effectively, if I make it a little bit smaller, this is effectively my solution. Okay, this is what my graph of y against t looks like. Now, I've got no idea what my function y is. Y will be a function in terms of t. Let's call it y as a function in terms of t. I've got no idea what that function is, but I know its behaviour, and that's enough. I don't need any more information. All right?